Right, H&C assignment 2. This is your assignment 2 past questions. First question, that is 1.1. The primary of an ideal transformer, shown in the figure, is connected to an AC supply of A volts. Now, we choose from the table that's given number 3. So A volts is 60 volts. So the primary, if I just draw the transformer here, the voltage A here is 200. Sorry, in this case is 60 volts. And you have the resistor here connected to the output secondary. So the primary is connected to 60 volts, secondary is connected to the load resistance of 68 ohms. Primary is 1500 turns, and the secondary 1200. So if I just say N1 is 1500 and N2 is 1200 turns. Right, what it's asking is the secondary voltage. What's the secondary voltage? So the formula that applies to all transformers, whether they are like primary, secondary transformers or auto transformers, is the same, and that is N2 over N1 equals V2 over V1 equals I1 over I2. Or you could write it the other way. You could say N1 over N2 equals V1 over V2 equals I2 over I1. So I is always opposite to the voltage and the number of turns. So from this first part, we can find out the secondary voltage V2. If you want V2, you should just transpose that. V2 is V1 times N2 over N1. From that we can say V1 is 60 volts. 60 times N2, 1200 over 1500. And from that you will get 48 volts. You just double check the answers. If I've miscalculated that, you just double check that and put your own values there. The second question is the secondary current I2. So this current I2, what's the current? If we have found the V2, which is 48, then we can find I2 because we have the resistor. Just carry Ohm's law, from Ohm's law, I2 is V2 over R. That is the R load resistor, RL, load resistance. So RL, that is 48 over 68, and my calculations say it will be 0.72 amps. No, 0.71 amps. Like I said, if you find different values, then you need to use the correct values, but this is the procedure. The third, number C, the primary current I1. So now we want to know how much I1 is. Then if we have I2, if we put that in this formula, either using N2 over N1 equals I1 over I2, or V2 over V1 is I1 over I2, then we can find the I1. Because N's have been given, I would use N rather than V1, V2, because we found V2. If we found this wrong, then I would be wrong as well. So I'll just go with N and say N, let's just rewrite that, N2 over N1 equals I1 over I2. And from that, if you transpose for I1, I1 is I2 times N2 over N1. And if you put the values there, 0.71 times 1200 over 1500. Again, my values, my calculation will give me 0.568 amps. Don't forget the units, volt, amp, amps. And then the next, or the last bit of that question is the load impedance or resistance referred to the primary, i.e. the impedance looking into the primary. So what it's saying, if you were to as far as the source is concerned, how much this resistance is from the load point of view, from the secondary of this transformer point of view. If you look at it from here, obviously it's 68 ohms. But from this source point of view, from the primary, how much that resistance is, because you are now bringing in to the equation the impedance of the transformer, and to do that you need to convert this by basically transfer this to the primary, and to transfer that you use this formula R.L. I'll just name this R.L. prime because it's transferred to the primary, is R.L. over N two over N1 squared. So R.L. prime is 68 over 1200 over 1500 squared. Be careful with these fractions, because you have to make sure the answer is right in your calculator. To be 106.25 ohms. So from primary point of view, the 68 ohm is seen as 106 ohm and something. Right, that's the first question. That is a set formula, so if you want to transfer from secondary to primary, that's what you do. And if you wanted to go backward, then you have to just put N1 over N2. Then you just go deal from primary to secondary. But in this case, you just go from secondary to primary. So that's the first question done. Obviously, you have to explain all these. In your assignment. Second question. Now the transformer has a tapping switch on the primary side, so you can tap to different switch to different inputs or primary windings. So the transformer is shown as something like this. You have so you have this transformer with the taps at 1, 2 is almost in the middle, 2, 3 and 4. And then on the secondary you have just a normal secondary here. It doesn't matter where the secondary is, that's A, B, and it says the 240 volt is connected to the primary at terminal 1 and 4, and A volt is then produced at terminals A and B. So in this case we are connecting to this point 240 volts, so primary is 240 volts and secondary is A. From the table again, if we just look at the number 3, that's 60 volts. So it's the same as the first question, it's just got these taps at the primary part of the transformer, so there's no difference really. You just ignore these two taps and you have a primary, you have a secondary, and the primary winding 1 to 4 has B turns. So the primary has 1500, so this whole thing from 1 to 4 is N1 1500 turns. And how much is the secondary N2 to give you that 60 volts? So again, N2 over N1 is V2 over V1, so therefore N2 over 1500 equals 60 over 240. And from that, I just write down N2 is 1500 times 60 over 240, so 1500 times, you could just write it this way, 60 over 240, and that will give you 375 turns. And that is the number of turns on the secondary that you have to produce 60 volts. Then the next part of the question says terminal 1 and 2 are designed so that a 120 volt supply also produces 8 volts output. How many turns must be between 1 and 2? So now we're saying we want to switch this. It's like you have these appliances that work in the UK and in America. So we want to go from 240 to 120. So you have to switch that at the back of the appliance, a switch there to turn this to that. And here you apply now 120 volts. So now this is your primary, and 240 is gone. So this was the A part of the question. The B part, you now ignore the 240 volts. You only have that one to deal with, and in this case now again B. In this case you have N2 stays at this 60 volts as your secondary voltage V2 as it was in the first part, but your voltage primary is changed to V1, is changed to 120, and N1 we don't know. we want to find out. So now we use this formula again. So N2 over N1 equals V2 over V1. Or I could just flip the whole thing and write it N1 over N2, V1 over V2. It's the same thing. And if we want N1, which is the question in this case, N1 is V1 times, sorry, I'll write it in a different way. I could do it that way, but I don't want to confuse you. So just say N2 times V1 over V2. If you transpose that for N1, you'll find this is true. And then you put the values there. N1 is N2, which was what we found here, 375 times V1, 120 over 60. And that will be 750 turns. So from 1 to 2 has to be 750 turns to give you that many, that much voltage. And that is the second part of the second question. And what's next? Terminals 1 and 3 are designed so that at 220 volts also produces a volts output. So again, we ignore that one. For the third part, I'm just going to write it here, C. So we forget that part of the question, we finish with that one. I'm just going to stick to N1 and V1 all the time, all the way, but we separated each segment separately so they're not getting mixed up, so you don't have like N1 here and N1 there, all the same but different values. But we want to separate it. This is for this question, this is for this question, although it's N1 and N2 and V1 and V2, but they're all different values. It's just one question turned into different segments. So now we want to apply the voltage. Instead of those two, we want to apply to these two, and that is going to be 200 instead of 240. It's going to be 220 volts. So it will also work in European countries. So it will be some sort of appliance that will work in America, Europe, and UK. But everywhere you go, you have to switch the tap to the right location. So 220 volts, that is your V1 now, and we want to find out the number of turns again between 1 and 3 to see how much that is to give you the same voltage. Again, you use the same formula. I'm just going to write this the other way. I've been saying you could write it, flip it, the whole thing, the whole equation around and write it that way. I'm just going to write that way. It doesn't matter. You could write it this way. You'll have to get the same answer. You'll get the same answer, and you have to follow the same procedure. But for the sake of argument, I'm just going to do it that way, just to show you it wouldn't make any difference. N1 over N2 equals V1 over V2. As long as you flip both sides, it doesn't make any difference in the final answer. So N1 is N2 times V1 over V2. So N1 is N2 we found N2 was 375. That is fixed throughout the whole question, because we found we want to give that 60 volts. We're not changing that. That doesn't have a tapping point. Only the primary has the tapping point. So N2 375 times V1 220 now over V2 60 volts. If you do the calculations, you should get 1,375 turns, and that is that for the second question. So you've done. So that's question 1 and 2 done for you. It's basically all you have to do is now to convert all this to the Word document and explain each part as to what you're doing. That's all. The same as what I've explained here. Okay, for the second question, number 2.1 is giving you this circuit and it says use the values from the table. I'm going to stick to number 3 again. So the value for L1 is 850 millihenries. That is 850 millihenries, or you could just convert that straight away to henries and say that is 850 times 10 to the power of minus 3 henries. Inductors are measured in henries. That is an inductor, basically a coil. A coil is an inductor. And in AC, they react differently than DC. So the voltage is given 100. So the voltage is 100 volts. AC at the frequency is, if I just say F frequency is 60 Hertz. It's given in the diagram. And the value of the inductor I got it from the table for this question. So now we need to find, first of all, inductive reactance. What is an inductive reactance? This is the inductance. Inductive reactance is XL. XL is measured in ohms, and to basically convert it to a value, to something that we can measure the whole impedance of the circuit in ohms. Resistance is already in ohms, 2 kilo ohms, and the inductance is given in henries or millihenries. We have to convert that to henries first and then convert it to something that is measured in ohms. And to do that, we are converting it from inductance to reactive inductance, XL. Reactive inductance. And that's XL, is shown by XL, and it's measured in ohms. The formula for XL is 2 pi FL. All of these are times 2 times pi times F frequency times L being the inductance. XL is 2 pi frequency, just say times 60, let's put times here, times L 850 times 10 to the power of minus 3, and the value should be 320.44 ohms. So that is the inductive reactance. That's the first part of the question. second is the total impedance as a complex number in both polar and rectangular. To write the impedance in polar and rectangular format, the way you have it, you can just easily write it in rectangular format straight away, because XL is always J, and you can just write that. Z is impedance, so this was part A, B. Z is impedance, that is R plus J XL. That is just the formula to write the impedance in the rectangular or Cartesian format. If it's XL, it's J. R doesn't have R. R is the real value. XL or XC. If this was a C or capacitor instead of an inductor, it would be minus J. So J for XL and minus J for XC, which we'll get to in a different question. So to write that with values, Z is R 2000 or 2K. 2 kilo ohm is 2000. We're just going to convert them all into ohms, basic units. So 2000 plus J XL 320.44. That is the impedance in the rectangular format. So rectangular and then the polar format. To find basically what this is basically in the Cartesian diagram or plane. You have x here and y here. X and y here. This y is your imaginary. Usually, instead of saying x and y, they just put down j here. So if it's going up, that's j. If it's going down, it's minus j, and this is the real values. And on the real values, usually you have r, that is your resistance. And if it's up going there, it's XL. If it's going down, it's XC, which is for capacitors. In this case, you have 2000 R here, 2000 for instance, and 320 here, 320.44 XL, and that would be your impedance. This line would be your impedance with this phase angle. So we're just not dealing with that phasor diagram here in this question because it hasn't asked you, but just as an indication as to what you have actually done here. This is what you've done. Now we want to convert that to polar. That means instead of saying how much real value and how much imaginary value, how much R and how much XL, you say how much is the length of this vector or phasor diagram, as you say in electrical engineering usually, how much the length of this with how much angle. You can convert this using the calculator from polar to rectangular, rectangular to polar. There's two buttons there. It tells you rec. If you put down rec and put the, sorry, we want to convert it to polar, so we would have to say press pole. You have a button there, it says pole. You probably have to press shift that to write pole, and it opens a bracket. You type the first value, which is the real value, 2000, put comma, again you have to probably shift and comma, and write the imaginary value, the second value is your imaginary value, 320.44. You don't write J. J is already indicated as imaginary. So when it comes to the secondary, if you write it the wrong way around, it'll be all messed up. So that's why you have to make sure the real value comes first, the imaginary goes 320.44, the second value, because the calculator knows this is your imaginary, this is J value. So when you press enter, what it gives you is the size of this vector with and the second value is the value of the phase angle. But we're not doing it again. You can use that. You can use that calculator to just double check your answer. This is just a quick way to get the answer. But for the assignment, ignore that part. But ignore as in you don't write it in your assignment, but you can use that. It's a good tool to double check your answers. That's right, that's correct. So now we want to write that into the polar notation or polar format. This was rectangular notation, how much the real value is, how much the imaginary is. Now we want to say how much is this length and how much is the phase angle. Using trigonometry, we can just easily do that. So to find the vector, the size of that, I'll just draw this a little bit bigger so you can see if this is 2000, your R, and L or XL is here, and the resultant is this vector, and that vector with the phase angle theta or phi. So if you consider this right angled triangle, one side is 2000, the other side is XL 320.44, and you can find the length of the hypotenuse and the phase angle using trigonometry. The hypotenuse would be the vector, what you need for the Z value itself. Z impedance is the size of this vector, and that is square root of R squared plus XL squared. And you just do that and put the values there, 2000 squared plus 320.44 squared, and if you calculate that, you should get 25.5 ohms. So that is the value for the impedance itself. For the phase angle, if you just say theta is your phase angle, we use invert tan, say invert tan or tangent of phi is opposite over adjacent. Opposite is 320.44 over 2000 and that will be now invert tan of this phase angle is opposite over adjacent. That's how it is. Phase angle itself is now invert tan of this value. So if I just say invert tan, 320.44 over 2000, then that will be 9.1 degrees. Just make sure your calculator is on degrees rather than radians. So now we have the phase angle and we have the impedance itself. We can write it. This was the Cartesian or rectangular notation. The polar notation is polar notation. Z is 2025.5 with an angle. This is angle, this is not L, it's just a symbol for the angle, and that is 9.1 degree. That's how they write the polar notation. So polar notation is that, rectangular notation is this. So that was your B part. C, the total admittance. Now you have the impedance. Admittance is opposite to impedance. 1 over resistance, 1 over impedance, 1 over R is conductance, and it's measured in Siemens, and also impedance also the same. 1 over Z, which is measured in ohms. 1 over Z is admittance, and that's measured in Siemens. So we just do that. We just 1 over reciprocal value of Z will give you impedance. And to do that, we need the polar notation. To do that, 1 over, we need the polar. We can't do 1 over this. We can, it'll be more complicated, and we don't want to do that. It's easier to do it this way. So to use that notation is easier. But if I just wipe this part of A, and B as well, really. I'll just leave that diagram there. The value of Z in polar notation. Now we need total admittance. So if I just say admittance as A is 1 over Z, and that is 1 over 2025 with the phase angle 9.1 degree. The way you do this, you do the real values. This basically, the angle is 0. If you don't see any angle, that's 0. So what you do, you divide the division we've done with complex numbers. Put a lesson there, and you've seen it. If you haven't seen it, then this is how you do it. The argument divided by the argument of the other one, and the angles are subtracted if you're dividing. If you're multiplying, you multiply together and you add the phase angles. In this case, you're dividing, so 1 over that, 0 minus this. So the answer would be for the impedance 4.95 times 10 to the power minus 4 4.95 4.99 times 10 to the power of minus 4 with the angle minus 9.1 degree Siemens. And that is for that part. Next part is saying part D, total current in polar format. Total current in polar notation. So to do that, we just use Ohm's law, voltage divided by Z. So we have the Z. If you're dividing, it's best to divide with the polar notation anyway. So our format of voltage is 100. The phase angle isn't given. That means voltage is your reference. So the voltage is zero angle, zero really. So this was C. Yeah, this was for C. For D, current of the circuit is voltage over Z, and that is 100 with a phase angle 0 over, again, 2025 with the angle 9.1, and if you just divide that, 0.049, 100 divided by this, 0.049 with the angle 0 minus 9.1, that's minus 9.1 degrees. That is how much current amps in amps is going through the circuit. That's your current for the circuit in polar notation. Then we have to find out the voltage across the resistor, VR and VL, for the next two parts. For voltage across the resistor, right, we have the current times that resistor will give you the voltage across the resistor, and times this times XL will give you that again. But XL itself has 90 degrees, so you have to consider that one. So if I just do the resistor first, I'll show you. So E, V, R is R times I, that is 2000 times. 2000 doesn't have any phase angle because this resistor is the element in the circuit that doesn't cause any phase angle. So the phase angle is 0 times 0.049 with the angle minus 9.1, and that should give you .98 with the phase angle minus 9.1. What we do, we just times this by that, and the angles this plus the phase angle of this. The phase angle of this one is 0, so 0 plus that is just minus 9.1. If you forgot about how to do the complex numbers. So that's that one. EF is the next one, voltage of the inductance. VL is XL times I. Now, what you have to remember is XL causes that 90 degree phase angle itself. So, and it's positive, it's the J is not minus J. So, XL, we calculated somewhere, XL was 320.44. With the angle 90 degree, and put this whole thing, I'm just going to wipe all that. Put the whole thing in brackets, so the whole thing has to be times by, that whole thing times by current, again, brackets 0.049 with the angle minus 9.1. So now what happens, you times this one by that, the argument and the argent add together, 90 plus minus 9.1, so basically 90 minus 9.1, and the value will be, VL is 320.44 times 0.049 is 1 320.44 times 12.49 is 15.7, and 90 minus 9.1, that's the phase angle 80.1 degree, and that's degree, and that whole thing is this much volts for the voltage of the inductor. Sorry, 80.9 degrees. 80.9 degree. So the voltage of the inductor is 15.7 with the angle of 80.9 degrees volts. Right, so that is basically that one. Just double check. Right. If you wanted to double check the answers to see if these values of the voltage that you found, VR and VL, so this is your V, by the way, this is volts, that's volts, so that's for VR and this is for VL. If you want to make sure this is right, you need to add this and that together to, if you add them, so VR plus VL really, it's not required, it's not part of this assignment requirement, but to double check your answer, you could convert this to rectangular and convert this to rectangular and add them together because it's easier to add them that way. You can't add them this way. Actually, you can't actually add them this way anyway. So the best way would be convert this to rectangular notation and convert this one to rectangular notation. Add them together. VR plus VL in the phasor diagram, vectorial sum of them should equal to V supply. As far as the vector is concerned, these signs have to be on top of them to show this Kirchhoff's rule, which says the voltage drop across all the elements in a series circuit equals to the voltage of the supply. It still applies in AC, but you have to put these signs of vectors or phasor diagrams on top of them because they're added vectorially, not just algebraically. To prove that, like I said, it's not required in this assignment, in this question, but you could do that to just double check these answers are correct. You convert this to rectangular, add them together, it should be the same as 100. It might not be exactly because we've rounded some stuff, so if it's near enough, that's good enough. Now moving on to the next question, 2.2. That's still part of the past question. Using the values from table 2 again, figure 4, calculate these questions. So similar thing, exactly the same, similar thing, but instead of an inductor, we have a capacitor. So we have to, instead of finding the inductive reactance, we have to find the capacitive reactance and do the whole thing. Next question in your assignment 2 is the same as number 2.1. So this is 2.2. It's very similar to 2.1, but instead of an inductor or a coil, it has a capacitor in the circuit. So a resistor in series with a capacitor connected to a source of supply, AC source of supply. Again, the voltage is 100 volts. The voltage of the supply is 100 volts. The frequency is 60 hertz. Resistance is 2 kilo ohms. And capacity is given in the table. Again, I'm going to pick the number 3 from the table. Number 3 from the table for the capacitor is 2.9. Sorry, that is a question. 3 microfarad. So C is 3 microfarad. Don't write M. If you can't find the symbol for micro, it's mu, or just use U, a little u, F, microfarad, because that's times 10 to the power minus 6. If you put M, if you put small m, that means 10 to the power minus 3. It's a big difference. So this circuit is given. It says find the same things as the previous question. Capacitive reactance. For inductive reactance, XL, the formula was 2 pi FL. For capacitive reactance, the formula is XC equals, XC is the symbol, and the formula is 1 over 2 pi FC. F being the frequency, which is given, C is the capacitance in farad. So you have to convert that to 3 microfarad to farad. So that would be 1 over 2 pi times 60 times 3 times 10 to the power minus 6 to convert that to farad. And if you put the values there in your calculator, that should give you 884.19 ohms. Now we can find the impedance in ohms. In the forms of polar and rectangular instances, find the total impedance in both as a complex number in both polar and rectangular or Cartesian notation. So that was A, B is Z equals 2000. Because it's C, we put minus J. In XL, if it was XL with P, we would put plus J. Because it's XC, we put minus J. XC is 8.19. This is your Cartesian mode of notation. So this is this many ohms. That's your rectangular notation. C. Sorry, it's not C yet. We have to write this in polar notation. So for polar notation, like I said, if I just draw a sketch of a diagram, so this is R 2000 ohms, and you have about 884.19 minus J. So around here, 884.19. So now this time it's going down. The vector for impedance is here. So this is your the argument or the length of the phasor diagram for impedance, and that's your phasor diagram, the phasor for the impedance. So that is Z in polar format. So to write that, we have to find the length of the phasor or the vector and the phase angle. Use the trigonometry, consider this right angle triangle. You have this size of this side of the triangle and the size of this side of the triangle, and you can find the phase angle as well. So Z is square root of R squared plus XC squared this time. Previously we had XL, this time we have XC. Now you say, why don't we put minus XC? First of all, we studied in complex numbers. J, if you J itself is square root of minus 1. If you square that, it'll be minus 1. And then we don't want to consider that anyway, because we don't want to consider the complex, we just want to calculate the value of the length. And why do we put minus or plus here? It doesn't matter, no, because if you square it, minus will be positive anyway. So this is the formula for impedance. To find the impedance, length of the impedance, we've already got the rectangular notation. To find the length of the vector, so we can write it in polar notation. This is the formula using trigonometry or Pythagoras to find the hypotenuse of this right angle triangle. Or you could consider this right angle triangle, it don't make any difference. The value is 2000 squared plus XC 884.19 squared, and that should give you 2186.73 hours. What about the phase angle? Phase angle is invert tan of opposite over adjacent. Opposite is 884.19 over 2000. If you put that in your calculator, and by the way, sorry, it should be minus this value because it's going down. So invert tan minus that will give you minus 23.85 degrees. Again, make sure your calculator is set on degrees, not Fahrenheit. Again, make sure your calculator is set on degrees, not radians. So that is the value. It is important to put minus here because it's going down, and the angle is minus 23 degrees, as you see, is below the horizontal axis or x-axis. Otherwise, the rest of the calculations might be slightly wrong as far as the signs are concerned. Not the values will be right. So that is that one. The B, C is the admittance of the total admittance of the circuit. So if we just say admittance is 1 over Z, and sorry, we haven't written the Z value in the format of polar notation. So we found the value of the phase angle, we found the Z argument, we've got the argument, we've got the argent, we can write the Z in the polar notation. So Z is 2186.73 with the angle of minus 23.85 degrees. So this is your polar notation. You could get to this from that to this without all this using your calculator. Well, like I said, that is not something you use for your assignment. That's something you would use just to make sure your answers are right for yourself. Just to double check your answers. So what you would do, you would just use shift polar 2000 comma minus 884.19. Press, you'll get this value and that value. So that's that. But this is how you write it in your assignment. That's admittance is 1 over this one, polar notation, we don't want the rectangular because it will be difficult to do 1 over that. So 1 over 2186.73 with the angle of minus 23.85. This is basically 1 with the angle of 0. So just if you can remember your complex numbers. So you do the argument of this one, 1 over the argument of this one, 2186.73. You put the value there, that is, in this case, that's 1 over 2186.73 will be 573 times 10 to the power of minus 6, and the angle 0 minus 23.85, that is with the angle positive 23.85. So this is your admittance in Siemens. That's measured in Siemens. So that's ABC done. For D, E and F, I have to wipe this whole thing to give us space. So now we want to find the current in the circuit, I. This is D part, I is voltage over Z, 100. The voltage is reference because it hasn't given you any phase angle, so the phase angle is 0 over the impedance, and the impedance we had in the polar notation was 2186.73 with the angle minus 23.85. And if you do the calculations, your current would be 0.04 5 with the angle of 23.85 amps. So how did we do this? 100 divided by this part will give you that. 0 minus 23.85 is positive 23.85. So in divisions for complex numbers, in the polar notation, basically you divide the arguments just as normal. 100 divided by this, you get the value of the argument, and for the arguments or the angles, you subtract the top from the minus, from the bottom. So 0 minus that. That's that. So that's number D. And E says find the voltage across the resistor, and F says find the voltage across the capacitor. Again, for voltage across the resistor is Ohm's law, still applies. That is resistor times current. Resistor is 2000 and our current is that. And it's in polar format. We don't have to convert it to rectangular because it's easier to multiply in polar notation. and if you don't remember how to do that, you just again multiply this value by this and add the phase angles in multiplication. In subtraction we subtract the phase angles. In multiplication you multiply the first bits together, and for the phase angles you just add them. This phase angle, if there is nothing there, that means it's 0. So 2000 by 0.045, 90, and the phase angle is 23.85, and that's how much volts, which is degree volts, is across resistor. VL is VC. You should make sure this is the right indices there. VC equals XC times I, and we've already calculated XC, and that was 884.19 with the angle minus 90 degrees. We have to put minus 90 degrees here because it's XC, as we said, it's going down. For XL was going up, it was 90 degrees. For XC is minus 90 degrees. It's just a rule. We just have to do that. Times that current 0.045 with the angle 23.85, and what you do, you multiply this argument by this argument and add this argent with this argent, or this angle with that angle. They call this part of this element is usually called argument. That element is called argent, or just say phase angle. So VC is if you do the calculations, it should be 39.78 with the phase angle, minus 90 plus 23.85 will give you minus 66.15 degrees. Don't forget the minus. And that is the VC. That was the R, and that's VC in volts. Again, same as the previous question, you can just convert these two to rectangular, add them together to prove that your values are right, because when you add them together according to Kirchhoff's voltage rule, it says voltage of the voltage drops across the series circuit, VR and VL, sorry, VC in this case. If you add them together, it should be equal to the voltage of the supply. You don't just add them algebraically. You can't just say 90 plus 39 or 40. That would be 130, around 130 volts. And you can see it's not 130 volts. But you have to convert that to, because you're not considering the angles. So you convert it to rectangular, you add them together, you'll have some real values, some imaginary values, and you'll see imaginary values will cancel each other, and you'll be left with the real values, because in this particular case, though, not always, in this particular case your voltage is with zero angle, so you don't have an imaginary value. I've just done that. Convert that to rectangular. That would be 80. This is not part of the assignment. You finished basically here. You finished. I'm just saying if you wanted to prove, that would be 82.31 plus J 36.39 in the rectangular format, and this one, if you convert that, it will be 16.08 minus J 36.39 minus J 36.39. Now if you add this and that together, you can see minus J 36.39, J 36.39, they cancel each other, so you're left with 16 here and 82 there almost, and if you add them it'll be 98.39, which is almost the same as that 100 volts. The reason it's not exactly is because of all the roundings that we've done with the angles, with the with all the values that we've done. So that's that one done. All the past questions have been done in this video, and you should be able to do that. Thank you.